Hasib Gan. Today I will talk about statistical mechanics, a few concepts on statistical mechanics, why it is needed, what are the classification, these things. And I will give some specific examples also. So first, let's take an example. Let's take a gas container. So this is a gas container, okay, and inside this gas molecules are there, and they can randomly move inside this container. Okay, now you can give information about these gas molecules. You can use the kinetic theory of gases from thermodynamics. You can say that this system has certain state that has pressure P, volume V, and temperature T. Okay, that's fine. Now if you want to talk about their motion, their configuration of the all particles inside this container, then Newton's law of motion cannot be sufficient to talk about individual particles. So let's say there is 10 to the power 23 number of gas molecules are there. Okay. So for each of that gas molecule, you have to write a second law equation, force equations. Okay. Or you can even use the Lagrangian equation, but on that case also the number of degrees of freedom will be very large. Okay, so this is very large system and it will be difficult to handle using this type of method. Okay, so Lagrangian equation and Newton's law of mechanics. Newton's law of mechanics can't deal this large configuration. So what we need to do, we need a statistic. So in classical mechanics we can deal with a large number of particles, and using this approach we can talk about their properties. So their position, momentum, their velocity distribution, energy distribution, these things we can easily infer from this. So first we need to talk about the classical statistics. What is it? So the gas molecules, these are the classical particles. So classical particles, they are characterized by phase space. So suppose there is a position coordinate, x coordinate, and momentum coordinate. So in the phase space, a point signifies that position and momentum coordinates of all the particles. So let's take it is at t equal to 0, and in subsequent time at t equal to t1 there is another point, and t equal to t2 there is another point. So this is basically a trajectory. Okay, trajectory in phase space. Now we can also consider it in real space also. Now let's consider it in uh, configurational space. So there are two particles inside this container. Let's take two. One of them is A and another is B. Okay, now suppose they are moving, and at a certain time they collide. Okay, so after collision the A particle suppose go towards this direction and B particle goes towards this direction. So you can individually follow the motion of both particles. Okay, so that's why they are called distinguishable particles. Okay, so distinguishable particles, this is the characteristics of classical statistics. Distinguishable nature. Okay. um, Now I will talk about quantum statistics. Um, I want to focus on this statistics. So quantum statistics, this is for the indistinguishable particles. Indistinguishable identical particles. Identical particles. So why identical? So why they are identical? So the particles have same mass, okay, same charge, same spin. Like take two electrons, okay. Also they are indistinguishable, okay. How they are indistinguishable? Let's take an example. So consider two hydrogen atom, okay, and hydrogen atom has one electron that is revolving around this nucleus. This hydrogen atom also has an electron that is revolving around it, okay. Now when these two hydrogen atoms come close to each other, then what happens? And then there will be a bond, okay, bond. And now at this hydrogen atom can be shared by this hydrogen atom also, okay. And electron at this hydrogen atom can be shared by this hydrogen atom also. So this electron is not fixed to this hydrogen atom, so there is some covalent bonding, okay. And covalent bonding means sharing of electron. So you can't tell that this electron, if you fix that this electron you have labeled by 1, you can't tell that where one electron is right now. It can be associated with this hydrogen atom, or it can be associated with this hydrogen atom. So this is the indistinguishable nature, okay. And it is the origin of the exchange interaction, so I don't want to talk about. But in today's video I want to illustrate a concept on quantum statistics, and that follows by this. So quantum statistics, there are two classifications of that, two types of statistics. One is Bose-Einstein statistics, and another is Fermi-Dirac statistics. Now, there are particles which are called bosons. They follow Bose-Einstein statistics. Boson have integral spins, like they have spin 0, spin 1, spin 2, like this. Like photon has integral spin 1, I think graviton has spin 2. These are all boson. Now, Fermi-Dirac statistics is followed by fermion, and these have half integral spin, like half, 3 by 2, 5 by 2. Electron has half in, electrons has spin half. Now let's see what is the distribution. So if there are some energy levels in a system, and this is the ground state, E0, this is E1, this is E2, these are the excited states. And if in this system there are n number of particles, okay, n number of particles. Now the distribution tells how the n number of particles are distributed in these energy levels, okay, okay, average occupation of each level. So these levels can have some degeneracy also, okay. So now I want to give the expression for that occupancy. So ng bar, this is the occupancy per energy state, and this is basically the probability. It tells the probability of occupancy. Probability of occupancy. And this is 1 upon exponential E minus epsilon j upon kBt. Now for quantum statistics, it can be either plus one or -1, these terms. Okay. Now this is the energy, and this probability tells, this NZ bar tells the probability of occupancy of the label which is having energy E, and this is the Fermi energy or chemical potential. So this is not the same thing. I'll make another video on this concept. What is chemical potential? So basically, you can think it as a statistical parameter. Okay, to understand these distributions. Now, for Fermi-Dirac distribution, this is +1, this term, and for Bose-Einstein distribution, this is -1. So from this formula, you can see that for Bose-Einstein distribution, the term in the denominator is less, small comparison to the term in the numerator, because there is a minus term in the Bose-Einstein statistics. Okay, the for Bose-Einstein I am writing down the formula. Okay, nj bar equals to 1 upon exponential epsilon energy minus epsilon, this is the chemical potential, epsilon j, divided by kbt minus 1. Okay, now why the occupancy per energy state is small in the case of Fermi-Dirac statistics? I want to talk about that. Okay, so to understand that, we need to understand also the Pauli exclusion principle. What is Pauli exclusion principle? So take any atom, and for this atom, okay, there are many electrons, okay, for this atom. Now for this atom, two electrons cannot have same quantum numbers. So what are the quantum numbers? That n, l, ml, ms. This is the principal quantum number. This is the azimuthal quantum number, the l, azimuthal quantum number, and these are the magnetic quantum number, ml, orbital magnetic quantum number, orbital spin quantum number. Okay, fine. So two electrons, for two electrons there should be one. So all the quantum numbers for two electrons should not be same. There should be at least one quantum number that should be differ. So according to this Pauli exclusion principle, let's take a d orbital. Uh, okay, we know that there are 5d orbitals, 1 2 3 4 5. So in 5d orbital, let's take an example of d6. So there are 5 upspin electrons. First we need to place them, and then there is another downspin electron. Okay, so you can see that in these are all orbitals. Okay, in a orbital there will be maximum number of 2 electrons. Okay, not more than 2. Okay, so this is due to the Pauli exclusion principle. Okay, Now consider the labels I have drawn before. Okay, there are few labels. These are the ground labels E0, and these are the excited labels. Okay, E1, E2, E3, and now suppose we have six particles of fermion, or you can take six electrons. Now you have to place these electrons on this state, on these labels. Okay, then what you will do? So first put two electrons here, then two electrons here, one up and one down, and here two electrons. Okay, so three labels we need to populate all those six electrons. Now do the same thing for bosons. Okay, so there are four labels. The condition is same for both these systems, and we have six bosons. Now what will happen? Now these six bosons all can take place here. Okay, in the ground state there is no such restriction. There was a restriction that not more than two particles, no two fermions can place in this, in any state. Okay, in every state there will be maximum two particles in each state, but here the occupation is not restricted. Here the six particles can be placed in the ground state. Okay, so this is the difference between the fermions and boson and the distribution. So this is the difference between fermion and boson and their distribution. Now I want to make a question, on a specific question, and let's try to under let's try to guess the answer. Okay, suppose you have a box of particles. Okay, and inside this there are, let's take, there is a box A which have fermions inside it. These are the fermions. Okay, and let's take another box that is B, and which have bosons inside it. Let's take same number of particles are there. Okay, and the other variables are fixed, um, like their volume is same, the container has same volume, and they are under same temperature. Now my question is, which box will be exerted by the particle, which box will show more pressure, whether Pa equals to Pb, or Pa greater than Pb, or Pa less than Pb. Let's think about it. So the answer will be, for fermions, so the answer will be, for fermions there is Pauli exclusion principle. Pauli exclusion principle. They follow Pauli exclusion principle. Okay, that means suppose there is an atom, okay, and one electron is there, that is attached with this atom, and another atom is just approaching towards this atom, okay, another atom, okay. Now uh, now whenever this atom will close to this atom, this electron over, now this electron's wave function will overlap to this electron's wave function, okay. Now depending on the spin, okay, there can be a repulsion Pauli repulsion. So that means suppose there are two fermions in the ground state or any state, okay, two fermions are there, one is spin up and one is spin down, and now if you add another particles, another electrons to this system, okay, that is spin up, or spin down, any of them. So whenever you will add that, it will create a repulsion. According to Pauli exclusion principle, it is not allowed. So it will repulse and it will not allow the electron to come to this position. Okay, so it will not allow. So suppose it has a spin up and this electron has also spin up, it will not allow to come this spin up electron in the neighborhood of this electron. In the layman language, I am trying to explain. So this is the thing. So there is a Pauli repulsion that is present for fermions, but for boson there is no such force. Therefore boson there will be attractive force. So uh, any number of particles can be available, can take place in this ground state, so there is some attractive nature of force. So due to this repulsive force, if you know that there is a repulsive force, then repulsive force that will generate pressure, that will generate pressure. So for the same systems, fermion, the box with have fermions inside it will generate more pressure, okay. So these are the concept I wanted to explain today. Please tell if anything. So if you have any doubt, please mention it in the comment box. Please like the video, and if you haven't subscribed, then subscribe the channel.